Today we're going to talk about two concepts. One is ions. Ions are chemical species that aren't neutral, so that's something new for us. And then the second thing we're going to talk about is drawing Lewis structures, not only for these ions, but then also for things that have more than a full octet, which can happen in some cases. Let's get started by defining ions. Ions are just simply chemical species that have an imbalance between the number of protons and electrons in their structure. One of the ways that this could happen is if we have more protons than we have electrons. The number of protons outweighs the number of electrons. This would be an example. If I have sodium, it has 11 protons because that's its atomic number. A neutral sodium atom also has 11 electrons. Now, if I took one of the electrons away and reduced this count to 10 electrons, I would now have one more proton than I had electrons. So instead of being neutral, this sodium would now have a 1 plus charge. That's an example of a cation. When the protons outweigh the electrons, the chemical species has a positive charge, and we call that ion a cation. There's another way that could happen. Let's take a look at chlorine. Chlorine is atomic number 17, so that means it has 17 protons. A neutral atom of chlorine has 17 electrons as well. But if I were somehow to change the count so that I had 18 electrons, now my electrons would be outnumbering my protons. And that means overall the species would have a negative charge. Like this chlorine has a 1 minus charge. Species that have negative charge are called anions. You can keep these two straight, cations and anions, by thinking about this. Cations have a plus sign, and the word cation has a T in it, and a T looks a little bit like a plus sign. The kind of ions that we're going to spend most of our time with today are called polyatomic ions. The word part poly in scientific naming means many or more than one, and atomic just means atom. So these are many atomed ions. An ion that contains more than one atom is a polyatomic ion. Here are some examples. SO4 2- is sulfate. It has 1 sulfur and 4 oxygens. And when it's all put together, there are 2 extra electrons. That's a polyatomic anion. Here's another one. CO3 2- is carbonate. 1 carbon, 3 oxygens. And when it's all put together, it has a 2- charge, or 2 extra electrons. Here's another one. Hydroxide. OH1-. 1 oxygen, 1 hydrogen, so it's polyatomic. But when it's all put together, there's 1 more electron than there is protons in the whole cluster. Polyatomic ions are a lot like molecules because they're covalently bonded together, but they have a charge, whereas molecules are neutral. So since these polyatomic ions are like molecules, we should be able to draw Lewis structures for them as well. So here are the rules for drawing Lewis structures for polyatomic ions. The first thing to do is give the dot symbols of all the atoms to be bonded, just like you normally would do. Let's say I had the ion carbonate, CO3 2-. Got a carbon in there, 4 dots. Got oxygen in there, oxygen's group 6, that's 6 dots. And there's 3 of them, so this would be a total of 18 electrons, and this would be a total of 4 electrons. So when I added this together, I'd have 22 electrons. So I've counted all my valence electrons and I have 22 electrons. Now here's where something's a little bit different for polyatomic ions. Remember, in anions there are extra electrons, in cations there are missing electrons. So we have to adjust the number of electrons to account for the charge on the ion. If I have an anion, I'm going to add electrons that are equal to the charge. So in that last one, CO3 2-, I had 22 electrons from my count from the 3 O's and the 1 C. But because this is negatively charged by 2, that means there are an extra 2 electrons. So really my structure needs to have 24 electrons in it. For cations, it's just the opposite. Because cations are missing electrons, I want to subtract electrons that are equal to the charge. Here's an example of a polyatomic cation, NH4 1+. It's called ammonium. Nitrogen, if I draw that dot notation, is from column 5. That gives me 5 electrons. And then I have 4 hydrogens. Hydrogens are column 1, so all told, that gives me 4 electrons. 5 electrons and 4 electrons is going to give me 9 electrons. However, this, because it's positively charged, is missing an electron. So because of that, I'm going to subtract 1 electron from my count, which leaves me with 8 electrons, and that's how many should show up in my structure. So then you make a skeleton structure. Just follow the same guidelines that you do for molecules. And then you fill up the octets, make sure that everything is surrounded by a full 8, except for boron, beryllium, and hydrogen, of course. And as is the case for molecules, if a structure has too many electrons, you might have to form multiple bonds, double or triple bonds. And then here's something that's different for ions. Once you're done and you've satisfied that your structure is what it should be, you want to surround it with square brackets, like this, and then indicate its charge. Let's try a few examples. First, I'm going to try hydroxide, OH minus, and show how that structure is formed. First thing I want to do is get my electron count. Oxygen is in column 6, so that means it would have 6 dots. Hydrogen is a column 1, so 1 dot. So I take these 6 electrons, add to this 1 electron, and that gives me a total of 7 electrons. But this is a 1 minus ion, so that means it's got an extra electron. So I'm going to add an electron to my count because of that. My structure, when I'm done, should have 8 electrons in it. Skeleton's easy because there's only 2 atoms, O bonds to H. Hydrogen doesn't need a full octet, but oxygen does. So I put 6 more electrons on the 3 remaining sides of oxygen. So now I do my count, 2, 4, 6, 8. That's the correct number of electrons. I'm supposed to have 8 electrons. So I'm done with my structure. The only thing I have to do now, because it's an ion, is enclose it brackets and indicate its charge. Let's try another one. Let's try this ion, sulfate, SO4 2-. At this point, you don't have to draw the dot notation probably every time. You can just look at the group number and do this quickly without drawing out the dot notation. I'm going to try that here. Sulfur I know is in group 6, so that should give me 6 electrons. Oxygen is in group 6 also, and there's 4 of them. 6 times 4 is 24, so that should give me 24 more electrons. So when I add 6 to 24, I get 30 electrons total. Now this is an anion. It has a 2- charge. That means 2 extra electrons. So I'll add 2 electrons to my count for a total of 32 electrons. That's how many should be in my structure. Now, skeleton, well, I'll put sulfur in the middle, surrounded by 4 O's. Sulfur is closer to the middle of the table. And remember our guideline that in a binary species, the first thing listed is usually in the middle, and then a compact symmetrical arrangement around that is the best choice. Sulfur has a full octet, oxygens don't. So I fill the octet on the oxygens by putting 6 more dots around each. Remember the idea of imagining a box around every atom. There should be a pair of electrons in each side of the box. And then I'll make my count. There's 6 electrons around each oxygen. So with 4 oxygens, that makes 6, then 12, then 18, then 24. And then I count the electrons in the bonds, 26, 28, 30, 32. So that's the correct number of electrons. Now this is a polyatomic ion, so I'm going to put brackets around it and put its charge, which was 2-. Let's do a polyatomic cation, NH4 1+. Nitrogen is in column 5. That gives me 5 electrons. Hydrogen's in column 1. That gives me 1 electron, but there's 4 of them. So that's a total of 4 electrons. When I add this all up, I get 9 electrons. However, this is a polyatomic cation. A 1+ charge means there's a missing electron. So I take away 1 electron and my count goes down to 8 electrons. Okay, now I need a skeleton. Well, hydrogen has to go on the outside, so there's only really one way I can do this. Put the nitrogen in the middle and put the 4 hydrogens on the outside. With those 4 bonds, nitrogen already has a full octet, and those 4 bonds represent the 8 electrons that I need in my count. So I'm done making my structure. I enclose it with brackets, and I indicate its charge. Okay, you try this one. Draw the Lewis structure for cyanide, Cn1-. Here's your answer. Carbon gives you 4 valence electrons. Nitrogen gives you 5 valence electrons. 4 and 5 is 9 electrons. But this is a 1- ion, so because of that, I'm going to add an additional electron, and that means my structure needs 10 electrons in it. It's only 2 atoms, so my skeleton's pretty easy. C bonds to N, and then I'll fill my octets and count. 2, 4, 6, 8, 10, 12, 14 electrons, which is too many. I'm only supposed to have 10. So I'm going to take a pair of electrons away, take that pair away, take that pair away, and then replace with another bond. And that's what we do when we have too many electrons. And then count. 2, 4, 6, 8, 10, 12. Again, too many electrons. So I'll take this away, another pair, put another bond in there, 2, 4, 6, 8, 10, and now I have the correct count. So let me just neaten this up a bit. There's my Lewis structure. I put square brackets around it and indicate its charge. Here's another one to try. Chlorate, ClO3 1-. Here's your answer. Chlorine is from column 7. That gives me 7 electrons. Oxygen is from column 6. There's 3 of them. All told, that's 18 electrons. 7 and 18 is 25 electrons. But this is a 1- charged ion, so I add one more electron, leave me with a total count of 26 electrons. My structure needs to have that many. I'm going to arrange this with the Cl in the middle and the 3 O's around it, kind of like the formula is telling me to do. Fill my octets. Each oxygen gets 3 pairs, and the chlorine gets 1 pair. And then I count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's the correct count. So I'm done drawing my structure. Put parentheses around it and indicate it's 1- charge. Here's phosphate, PO4 3-. Draw the Lewis structure for this. Here's your answer. Phosphorus is in column 5, so that gives me 5 electrons. Oxygen is in column 6, that gives me 6. 4 times is a total of 24 electrons. 5 and 24 is equal to 29 electrons. But this is a 3- ion, so I add 3 more electrons, and that gives me a total of 32 electrons. Incidentally, you may notice that we're always ending up with even numbers of electrons. Anytime that doesn't happen, you screwed something up, and you need to go back and check your work. You should always end up with even number of electrons in your structure at this point. Now let's make a skeleton. I'm going to put my phosphorus in the middle, surrounded with 4 O's. Phosphorus is already good. It's got a full octet, but the O's need 6 electrons each. Now when I do my electron count, I've got 6 in-lone pairs around oxygen, and there's 4 oxygens, so that makes 24 electrons. Then the bonds make 26, 28, 30, 32. That's the correct number. So again, square brackets and charge. One more, nitrate. Nitrate is NO3 1-. Here's your answer. Nitrogen gives you 5 electrons because it's in column 5. 3 oxygens, column 6, will give you a total of 18 electrons. And it's a 1- charge, so I'm going to add 1 more electron to account for that. And I end up with 24 electrons in my structure. Put nitrogen in the middle, surround it by 3 O's, and then fill octets. And the nitrogen needs 1 lone pair. Now when I make my count, I find I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons, which is too many. So I'll have to find 2 atoms that are bonded to each other, which means the N and any of the O's. Remove a lone pair from each of them, and then replace it with a double bond. Now, how do I know not to put it on the right-hand O or the left-hand O? I don't. I have options here. We're going to talk a little bit about what the implications of those options are in a bit. Sometimes the central atom in a molecule or a polyatomic ion, when you're drawing the Lewis structure, will require more than an octet. How do I know if I'm in one of those situations? Well, there are 2 ways. One of them is, sometimes the central atom, it's bonded to more than 4 atoms. So in that case, it would have to be surrounded by more than 4 bonds. Here's an example. Sulfur hexafluoride, SF6. When I draw this Lewis structure, I don't have any choice when I make the skeleton but to create an expanded octet, because the sulfur is bonded not to 4 fluorines, but to more than 4 fluorines. So I know I have to have an expanded octet there. Sometimes it doesn't seem obvious at first, but the structure they end up making doesn't account for all the valence electrons that are in the atoms. Here's an example of what I'm talking about. SF4, sulfur tetrafluoride. Let's draw the Lewis structure for that. Sulfur is in column 6, that gives me 6 electrons. Fluorine's in column 7, and there's 4 of them, so that'd be a total of 28 electrons. 6 and 28 is 34, so my structure should have 34 electrons in it. Make a skeleton. I put sulfur in the middle. I'll surround my sulfur by the 4 fluorines, Halogens like to be on the outside. And then fill octets. Sulfur is already good with octets. Fluorines each need 3 more pairs. So now I have stability. I have a full octets everywhere. Now I'll make my count. 2, 4, 6 for each fluorine. And there's 4 fluorines, so that's 24, 26, 28, 30, 32 with the bonds. Well, I've got all my electrons accounted for, but I'm supposed to have 34 electrons in my structure. When this happens, you put the extra electrons on the central atom in pairs. So with the extra 2 electrons I just put on that sulfur, I now have the correct count. This shows that I needed an expanded octet. I needed more than a full octet on sulfur. You can never do this for period 1 or period 2, the first 2 rows of the periodic table. Those nuclei are just not strong enough to support more than 8 electrons. But if it's period 3, 4, 5, or 6, those larger nuclei can have expanded octets when they're necessary. Another thing that comes up, we saw with that nitrate that we drew. Sometimes you can draw more than one Lewis structure. When we did nitrate, we might have ended up with what we did. It looked like that. Or we might have chosen to draw it a different way. We might have drawn it this way. Or we might have chosen the third option. In all 3 of these cases, the only thing that's different is where is the double bond. In the first structure, it's there. In the second one, it's there. In the third one, it's there. In cases where you have 2 or more structures and they differ only in the placement of where is a multiple bond, a double or triple, those are said to be resonance structures. In resonance structures, the actual molecule is not, it's not an either or. It's not one of the 2 options or the 3 options like we had in nitrate. Instead, it switches back and forth. The molecule jumps back and forth between forms, and it does it very, very quickly. Here's our nitrate. Here's what could happen with this nitrate to switch forms. That pair of electrons that's the double bond could jump up and become a lone pair, while at the same time, one of the lone pairs on that other oxygen switches positions and becomes part of a double bond. And that gives you this structure. Then that structure can morph as well. The double bond can be formed in a different place from a lone pair, and the pair that's making the double bond currently could become a lone pair on a different O, which would bring us to this form. And that form can morph as well. The electron pair that's part of the double bond becomes a lone pair. One of the lone pairs on the third oxygen now becomes the double bond, and then we're back to the original structure. Now what really happens is this happens many, many, many times a second. It alternates back and forth from one position to another, kind of like this, only way, 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 way faster. Sort of like watching the blades of a fan spin around. When the thing is moving, you can't tell that there's 3 blades or 4 blades on the fan. It just turns into a sort of a blur, and that's kind of what we have here. So sometimes the structure of a molecule that exhibits resonance is not shown as the 3 different options, but it's sometimes shown as just like a sort of an average of the structures. Like here's an example. With nitrate, we've got these 3 sticks that represent the single bonds, and then the double bond is shown as sort of dotted lines, and it kind of indicates that that double bond is all over the place. It's a concept known as delocalization. Here's another fairly famous example of this. This is called benzene. The name of this molecule is benzene. You might have heard of it before. Benzene can be drawn 2 different ways. It's a ring-shaped structure, which is a little bit weird. And it's got 6 carbons and 6 hydrogens. Every other bond is a double bond. Here it's drawn this way. Well, over here, the double bond is shifted over 1. So again, it's every other bond, but it's just a different bond. That's the double. Well, because it resonates back and forth and back and forth and back and forth and back and forth between these 2 structures over and over and over again, lots of times chemists will draw that structure this way. Instead of showing any 3 bonds as being the double bonds, they just delocalize it and use this ring to sort of indicate that the electrons, those extra 6 electrons that make the double bonds, are all over the place. That's resonance.